Hello there. In this presentation, I'll be talking about a technological framework to teach music online. The purpose of this research is to identify the essential elements of current online learning approaches used in academic music courses and critically consider their application in the development of an online pedagogical framework for online music courses. The research has two main questions. What are the key components to teach online music skills to music tutors? And the second question is how can these components be adapted to implement an automated online tool that can train itself based on different students' learning styles and skills. Now we are going to be looking at kind of state-of-the-art research in music technology today. What are some of the active problems and domains that people are working on in both academic and industrial related to our research questions? And the main part of this research dealt with chord detection. The basics of the framework are Train AI Tutor provides a music exercise using the music learning system. Learner uses interfaces for practice and learning, and then the learner uploads his or her video of exercises and music performance to the MLS. MLS sends the audio recording to music feature extraction and critics, where it's analyzed and further presented to the Train AI tutor for assessment. As an initial effort to address the chord detection problem, we had to find a comprehensive database first. We used the Battle album first, including 180 MIDI files along with their note annotations which would make the process of feature extraction easier. We reduced the annotation to 24 chord labels corresponding to main measure and minor chords. These labels are the predefined labels we had for each measure and minor chord. Let's dig deeper into the problem to see how we can extract features of an audio file. The first step to template-based approach is to convert the audio recording into a sequence of chroma-based audio features. These features can often be further processed, for example, by applying suitable smoothing filters to even out temporal outlines or by applying logarithmic compressions to enhance small yet relevant spectral components. The chromotype used may have a stronger influence on the chord recognition results. We illustrated this fact by considering three different chromotypes. STF-T-based chroma features with a small logarithmic compression, CQT-based chroma features, and then IIR-based chroma features with logarithmic compression. So in the chord detection process, first the audio recording is converted into a chromogram representation. We use the STFT variant. Second, each chromogram vector is compared with each of the 24 binary chord templates, which yields 24 similarity values per segment. These similarity values are visualized in the form of a time chord representation. Third, for each frame, there is a chord label N of the template that addresses the similarity value over all 24 chord templates. These yields our final chord recognition results, which is shown in the form of binary time chord representation. And then, finally, the manually generated chord annotation are visualized. Here is a representation of our template-based pattern matching. So these chords are represented here based on the template-based pattern matching. And here are the patterns that we defined. Overfitting problem in using template-based pattern recognition made us to think about convolutional neural networks. To improve our model, we collected more chords and we made 6,000 chords based on the piano that were converted to MIDI file, and we used them in our chord detection. We generated our own dataset, adding 4,000 chords in different intervals. In music, the term chroma feature or chromogram closely relates to the 12 different pitch classes. Chroma-based features, which are also referred to as pitch class profiles, are a powerful tool for analyzing music whose pitches can be meaningfully categorized and whose tuning approximates to equal tempered scale. We use this technique to extract data from our files. The deep convolutional neural network architecture proposed in this study is comprised of three convolutional layers interleaved with two pooling operations followed by two fully connected layers. The proposed CNN architecture is represented in this figure. Confusion matrix, as the name suggests, gives us a matrix as output and describes the complete performance of the model. There are four important terms. True positives, meaning the cases in which we predict yes and the actual output was also yes. True negatives, the cases in which we predicted no and the actual output was no. False positives, the cases in which we predicted yes and the actual output was no, and false negatives, the cases in which we predicted no and the actual output was yes. And here is a representation of the accuracy of our chord detection. And since this project is an ongoing project, we are going to add score following, and the impact of this project is going to benefit underrepresented and students with disabilities to express their feelings better.